Vibration analysis of FG plate. Abstract. In this article, vibration response of functionally graded material, FGM, plates are investigated by finite element formulation. By applying the Hamilton-S principle, the governing equations of the FGM plates are derived based on the first-order shear deformation theory. The FGM plate is modeled by using 9-noded heterosis element by incorporating the effect of rotary inertia and shear deformation. 9-noded heterosis plate element is used to formulate the elastic stiffness matrix and mass matrix. The results are also extracted from Abaqus CAE by using S8R5 shell elements. Free vibration analysis is done to obtain the different modes as well as the frequencies. Harmonic sine load is applied at the center of the FGM plate to obtain a forced vibration response. Impulse forces of rectangular, triangular, and half-cycle sine shapes are applied on the top of the plate at the center, and the response spectra of C-Si C FGM plate is plotted. Keywords: FGMS, finite element method, heterosis plate element, response spectra. 1. Introduction. The diverse and potential applications of FGMs in aerospace, medicine, defense, energy, and other industries have attracted a lot of attention recently. The concept of functionally graded materials, FGMs, were first demonstrated by a group of scientists in Japan in 1984 during a spaceplane Project 1. Combination of materials used here served the purpose of a thermal barrier system capable of withstanding a surface temperature of 2000 K with a temperature gradient of 1000 K across a 10 mm thick section, JETAL2. Later, its applications have been expanded to also the components of chemical plants, solar energy generators, heat exchangers, nuclear reactors, and high-efficiency combustion systems. The concept of FGMs has been successfully applied in thermal barrier coatings where requirements are aimed to improve thermal, oxidation and corrosion resistance. FGMs can also find application in communication and information techniques. Abrasive tools for metal and stone cutting are other important examples where the gradation of the surface layer has improved performance. It has been found from the literature that not many studies are done to the vibration analysis of functionally graded plates. B. Sideretti et al. 3 carried out the free vibration analysis of functionally graded plates. The variations of the volume fractions through the thickness are assumed to follow a power law function. The Reisner-Mindlin first-order shear deformation theory is very much appropriate for thick plates for it was taken to analyze the behavior of the plate subjected to free and forced vibration. They have developed analytical formulations and solutions for the free vibration analysis of functionally graded plates using higher-order shear deformation theory, HSDT. The principle of virtual work was used to derive the equations of equilibrium and boundary conditions. Navier's technique was used to obtain the solutions for FGM plates. Jyoti Vimal et al. 5 have studied the free vibration analysis of functionally graded skew plates using the finite element method. The first-order shear deformation plate theory is used to consider the transverse shear effect and rotary inertia. The properties of functionally graded skew plates are assumed to vary through the thickness according to a power law. It is found that when the length-to-thickness ratio of functionally graded skew plates increases beyond 25, the variation in the frequency parameter is very negligible, and also found that a volume fraction exponent that ranges between 0 and 5 has a significant influence on the frequency. M. and Gulshan Taj et al. 6 carried out a free vibration analysis of functionally graded material, FGM, skew plates subjected to the thermal environment. It was concluded that the volume fraction index and skew angle plays an important role in predicting the vibration of FGM skew plates subjected to thermal load. J. and Reddy 7 have studied theoretical formulation and FEM model based on Tsdt for FGM plate. The formulation AC counted for thermomechanical effects combining change with time and geometric nonlinearity. In this higher order theory, transverse shear stress was expressed as a quadratic function along with the depth. Hence this theory requires no shear correction factor. The plate was considered as the homogeneous and material composition was varied along with the thickness. The Young's modulus was assumed to vary as per rule of the mixture in terms of the volume fractions of the material constituents. Hughes and Cohenate developed the heterosis element and elemental equation. They derived lumped positive definite mass matrix, element matrix, and load vector and method for finding critical time step. High accuracy finite element for thick and thin plate bending is developed, based upon Mindlin plate theory. It has been found from the literature survey that not many researchers attempted to the vibration analysis of functionally graded plates. Further, we observed that many authors could model such problems with a stepped variation in material properties instead of continuous variation. This would have happened because of the limitations of the commercial software available. In this context, we felt that Matlab code could be used for tailoring the continuous variation in material properties in FE modeling. Hence Matlab code was developed for vibration analysis of FG plate. The analysis was carried out for C-Si C FGM plate with different volume fraction indices. The results are compared with Abaqus CAE by using S8R5 shell elements. 2. Problem formulation. First-order shear deformation theory is used for plate formulation. Displacement variation is linear, across the plate thickness. But there is no change in plate thickness during deformation. A further assumption is that the normal stress across the thickness is neglected. Properties are graded through the thickness direction, which follows a volume fraction power law distribution. The different elements of the plate are expected to undergo translational and rotational displacement. In the present work, 9 noted heterosis element is used to discretize the plate. 2.1 Strain displacement relations. The displacement field at any arbitrary distance z from the midplane based on the first-order shear deformation plate theory is given by 2.2 Finite element formulation. In the current work, the FGM plate has been discretized using 9 noted heterosis element with 5 degree of freedom, DOFs, at all the edge nodes and 4 DOFs at the internal node as shown in the figure 2. The serendipity shape functions have been used for the transverse DOFs, W, and Lagrange shape function are used in the remaining DOFs, U, V, X, and Y. 2.3 Resultant forces and moments. The analysis of FG plate is carried out to establish the relation between the forces and strains by considering transverse shear terms, where represents the in-plane stress resultants, N, out-of-plane bending moments, M, and shear resultants, Q. Here, C is the constitutive matrix 9 of the FGM plate. To compensate for the parabolic shear stress variation across the thickness of the plate, a correction factor of 5/6 is used in the shear coupling components of the constitutive matrix 10. Using green Lagrange S strain displacement expression 11, the linear strain displacement matrix B have been worked out. Txyxyxyxyxyxyznnnnmmmmqq equals. The different participating element level matrices such as elastic stiffness matrix, and consistent mass matrix have been derived using corresponding energy expression. Ek. M. The element elastic stiffness matrix and element mass matrix are derived using the following relations. 11, Te11 KBCBJDD11 equals, dash. 12, Te11 Ninjade11, equals, dash. In which, I is the inertia matrix. 2.4 Computer coding and implementation. A computer program is developed using Matlab to implement the finite element formulation and include all the necessary parameters to investigate the vibration behavior of the FGM plate. In the present code, selective integration scheme is incorporated for the generation of the element stiffness matrix. The 3x3 Gauss quadrature rule is adopted to get the bending terms, and 2x2 Gauss rule is used to solve shear terms to avoid possible shear locking. The mass matrix is evaluated by using 3x3 Gauss rule 12. 2.5 Formulation of dynamic problems. Stiffness matrix is validated by bending problems and mass matrix is validated through vibration problems. In order to validate the formulation of mass matrix, one has to solve a free vibration problem by incorporating the validated elastic stiffness matrix. The standard governing equation in matrix form for the deflection problem is 3 results and discussion. The properties of FGM plates are graded through the thickness direction according to a volume fraction power law distribution, figure 3. 3.1 Free vibration analysis. The heterosis element is used in the code for free vibration analysis. For validation of the present code, the data available for the functionally graded plate aluminium oxide titanium alloy of size 0.4 mx 0.4 mx 0.005 m available in the literature of HETAL13 is used. In numerical simulation by Abaqus, S8R5 element has been used. Table 1 shows the material properties. Table 2 validated the code with literature and simulation. Table1 material properties of aluminium oxide titanium alloy FGM plate. Table2 variation of fundamental frequency with n values. Cantilever FGM plate comparison. N. The present code is validated with results of HETAL 2001. The simulation results are also in good agreement with results obtained from FEM coding. This ensures the correctness of the formulation of the stiffness and mass matrix. 3.2 Free vibration analysis of C-Si C plate. The analysis is done for C-Si C plate, 0.5x 0.5x 0.001 m. Material properties are given in Table 3. Convergence results are shown in Figure 4. First 4 mode of vibration shown in Figure 5 by Abaqus using S8R5 shell element. Frequency of vibration is minimum for carbon plate as shown in Table 4. Table3. Material properties C-Si C FGM plate. Material. 3.3 Forced vibration analysis. Forced vibration analysis was carried out at the center of the plate using harmonic sine loading and different impulse loadings. 3.3.1 Harmonic sine wave loading. A harmonic force P, T, equals P0 sin, load is applied at the center of the plate, figure 6, A, 6, B, where P0 is the amplitude or peak value of the force and is the forcing frequency. Is the forcing period of the FGM plate P0 equals 1 n and equals where is circular frequency and is natural frequency of the plate. Table 5 compares the undamped and damped cases. Figure 6, C, for simply supported plate. The maximum displacement at the center of the fixed plate as shown in Figure 6, D, is less than that of simply supported plate. Fig 6 shows that maximum displacement at the center of the plate increases with the material index, n value, T. 3.3.2 Impulse loading. A very large force that acts for a very short time but with a time integral that is finite is called an impulse force. Impulse forces of rectangular, half-cycle sine, triangular shapes each with the same value of maximum force 1n is applied at the center of the plate. The response behavior of FGM plate is studied for material index, K, value equals 2. Td is pulse duration. The response spectra of the FGM plate with material index n equals 2 is shown in Figure 7. Tn is the natural time period of vibration of the plate and T0 is the static deflection of the plate. Static deflection is 1.438 e4m and natural time period is 0.0365 seconds. Table 6 presents the variation of deformation response factor, RD, with Td/Tn values, n equals 2. The present results are in good agreement with the available literature. 14. For conclusions. In the present study, an FE solution is obtained for free and forced vibration analysis of FG plates using heterosis element. The analysis is carried out by developing a computer program in Matlab. A 9-noded heterosis element is used to model the FGM plate. The heterosis element exhibits improved characteristics as compared to the 8-noded serendipity and 9-noded Lagrange elements. It offers a high level of accuracy for extremely thin plate configurations. Convergence study has been carried out for ensuring the convergence of the numerical results. The results are also extracted from Abaqus CAE by using S8R5 shell elements and are in very good agreement with the developed elements. Free vibration analysis is done to study the different modes as well as frequencies. It is observed that free vibration response is minimum for carbon and maximum for silicon carbide plate. The central deflection of the plate increases with increase in volume fraction index for all types of boundary conditions. From the response spectra, it is clearly understood that if the pulse duration, Td, is longer than Tn/2, the overall maximum deformation occurs during the pulse. Then the pulse shape is of great significance. For the larger value of Td/Tn, the overall maximum deformation is influenced by the rapidity of the loading. The rectangular pulse in which the force increases suddenly from 0 to maximum show the large deformation. The triangular pulse in which the increase in the force is initially slowest among the three pulses produces the smallest deformation. The half-cycle sine pulse in which the force initially increases at an intermediate rate causes deformation that for many values of Td/Tn is larger than the response of the triangular pulse. Sufficient duration steep loading produces a magnification factor of 2 and gradual loading increase results in a magnification factor of 1.